Welcome again. We are going to continue our discussion about Newton's laws and look at a few more examples today. Last time we discussed this idea of pulling a car with a truck, and we were trying to quantify what the tension in the cable might be. And we went through that, and we introduced the idea of a tilted coordinate system to help us minimize the number of vectors that we need to resolve into components. And then with this tilted coordinate system, we analyzed what was happening in the y direction and the x direction, and we were able to deduce that the tension in the cable would be 16,800 newtons. We moved on to part B to determine the most massive car that you could pull with this cable, and we continued using the tilted coordinate system for this, and we're able to find a mass of 1880 kilograms. Again, if you're struggling at all on this particular problem, remember that I have another video example where I go through this step by step on the whiteboard, and maybe that'll help make sense for you. When you have a good grasp of how to solve a problem like this, then that will unlock your abilities to tackle similar problems where we need to apply Newton's laws on an inclined plane. So let's do another example like this where we use an inclined plane and there are two masses involved, but instead of towing a truck, now we are connecting these two masses via a pulley to one another. And what our objective is to angle this ramp in such a way that mass 2 is going to slide down the ramp at a constant speed. Remember that jargon again, constant speed tells you acceleration equal to 0. Okay, so in order to do this, let's draw a free body diagram for each mass individually and see how they work together. So the free body diagram for mass 1, let's go back a second. Mass 1 is the one that's hanging here on the left-hand side. That free body diagram is relatively straightforward. We've just got the tension pulling up on the mass and the weight force pulling down. Because both of those forces are pointing in the vertical direction, it's sensible to just use a traditionally oriented coordinate system for this mass. I'm free to choose any coordinate system for these masses independently, and so I don't need to use a tilted coordinate system, nor do I necessarily want to, because these forces that are involved align quite naturally in the vertical direction, so I might as well keep my y-axis in the vertical direction. When I go ahead and then apply Newton's laws, again, it's a pretty straightforward thing. Nothing is happening in the x direction, and in the y direction, since my acceleration is equal to 0, this goes away, and when I sum my forces in the y direction, I get the tension force pointing in the positive y direction and the weight force pointing in the negative y direction, okay, equal to 0 since the acceleration is equal to 0, which then allows me to deduce that the tension on the rope should be equal to mg, where we're using mass 1 here. Sorry, I just realized this should also say mass 1, not mass 2. Okay? All right, so that's pretty straightforward for the first mass, but let's go back a second. The second mass is on the inclined plane, so we may not necessarily want to take the same approach of using the traditionally oriented coordinate system for mass 2. Let's draw the free body diagram to start with, and what we can see on this free body diagram is that we've got the tension pointing along the ramp, up the ramp, right? The ramp goes like this, and the normal force is perpendicular to that surface, and the weight, as always, is going to point down. So for this mass, two of the three forces are oriented in such a way that a tilted coordinate system would be more advantageous, because now with this coordinate system choice, I do not need to resolve the normal force or the tension force into components. I'm only going to need to worry about that with the weight force. So if I apply Newton's second law to this mass and sum my forces in the x and y direction, setting those equal to mass times acceleration, where acceleration is equal to 0 in both directions. Then I get the normal force. In the y direction, I get the normal force pointing in the positive x direction, the component of the weight force pointing in the negative y direction, which in the last lecture we talked about why it is that is going to be equal to a cosine rather than a sine. So if you're not too clear on that, just make sure you review that this is my theta. So my weight component that is pointing in this direction, this is the weight component in the y direction, that's adjacent to this angle, and so I need a cosine function. Okay, solving this equation, I get that the normal force is equal to mg cos theta. And then if I repeat the same process in the x direction, making sure that I account for the total forces acting in the x direction, which is the tension force in the positive x direction, and the weight force in the negative x direction. Actually, the way that this coordinate system is defined, I really should have said that this is the positive x direction, and this is the negative x direction. If I'm going to put positive here, it doesn't really matter because when we solve it, we get tension on one side. As long as there's a sign difference here, we get tension on one side and the component of the weight force in the x direction on the other side. Okay, so we might be wondering at this point, okay, I've got right now 3 equations. Okay, what do I do with these? Remember that we're trying to solve for the angle theta that's going to achieve the condition that the mass 2 slides down the ramp at a constant speed. This equation by itself contains theta, but we don't really know yet what the normal force is independent of that, so this equation has 2 unknowns in it. This equation doesn't involve theta at all, and this equation does, but it involves tension, which we also haven't solved for. However, when we talked about tension, remember that the tension, it is undiminished throughout the length of the rope. So if we look back here, the rope or the cord is connected from mass 1 to mass 2. Therefore, the tension on mass 1 is going to be equal to the tension on mass 2, which means that I can substitute the equation from the first mass into the second mass and replace that tension with m1g. That allows me then to solve for the angle theta as being 12.5 degrees. Okay? So this is another example of an inclined plane problem. The difference here is that for one of the 2 masses, I chose to use a traditionally oriented coordinate system, and for the other, I chose to use a tilted coordinate system. So you have to think about each problem and look at what's advantageous for the situation. So I'm going to do a more complicated inclined problem or tilted problem for us to carefully think about what we need here. So suppose that you are racing a motorcycle around a bend, and you know that there's a certain friction between your tires and the road surface. And you know that frictional coefficient is going to be equal to this value here. We also know what the radius of curvature is for this bend, and what we want to know is what is the maximum speed I can take this bend without sliding out. So we can approximate this as some sort of circular motion. And remember that if I am changing directions, then my velocity is not constant. I'm going to have acceleration in the form of centripetal acceleration. And to refresh your memory, when we talked about centripetal acceleration, we used this equation, v squared over r. And if I know r, and I can use Newton's laws to solve for a, then I can come up with this value v of how fast I can take this curve. Okay, so let's make a free body diagram of the motorcycle. The weight forces, as always, pulling down on the motorcycle. The normal force, if the road surface is horizontal, is pointing directly up, and the friction force is pointing in towards the center of the circle. So you have to kind of picture this in 3 dimensions, even though we're really only going to use these 2 dimensions. This is the center of the circle, so you can imagine the motorcycle coming out like this and around the bend and so on. So this is the center of the circle. Okay, so with that free body diagram, it's clear that it may not benefit me. Although the motorcycle was leaning in at an angle, it doesn't appear that that's going to benefit me to use a tilted coordinate system. All of these forces align themselves quite naturally along either the x or y axis of a typical traditionally oriented coordinate system. So I'm going to choose to use this coordinate system instead. Okay, when I go ahead and apply Newton's second law and I sum the forces in the y direction, I've got the normal force in the positive y direction, and I've got the weight force in the negative y direction. Why are they equal to 0? I just said there's acceleration involved. Yes, there is acceleration involved, but you're not going in a curve up and down, you're going around the bend this way. Right? So in terms of the y direction in this coordinate system, there's no acceleration. You are hopefully sitting still on the surface, not jumping up off of it or accelerating into it. You just are stable and equilibrium. And so that's why this y component of the acceleration is going to be equal to 0. When I solve that equation, then I just mainly conclude that the normal force is going to be equal to the weight force, which I can also see just looking at my free body diagram, assuming that I've drawn it correctly. Okay, so let's look now in the x direction. In the x direction, remember this equation is what we're ultimately going to use once we figure out what's going on with the acceleration. So it looks as though I've only got one force that's relevant. This frictional force is what's providing what we would call the centripetal force. And so in that direction, in the x direction, when I sum up my x components and I set them equal to m of the motorcycle times a, I can replace this centripetal acceleration in here, and the only thing that appears in my sum then is the frictional force. Okay, so what then do I replace this frictional force with? Okay, well, we know from the definition of friction that it's going to be equal to mu times the normal force. Okay, now from the previous step, we were able to figure out what the normal force equaled. It wasn't anything fancy like we would have on an inclined plane. It was simply equal to the weight. So in this case, then, I want choice D, that I'm going to replace F sub r m with mu s times the weight mg. Okay, so putting this all together, then, I take this equation that I had on the previous page and I replace the frictional force with mu times the normal force, which is equal to mg. And now I can see that a lot of things, well, maybe not a lot of things, but the mass itself actually cancels. So it won't matter what the mass is. In the picture, I had a second passenger on the motorcycle. That won't matter for this case. The only thing that's going to matter in terms of figuring out this velocity is what is the frictional coefficient and what is my turning radius. G is just a constant. This should be sensible, right? If I'm on a slippier surface, then I'm going to need to slow down. If I am taking a really tight turning radius, then I'm going to need to slow down in order to navigate that. Okay, so it's sensible is what I'm arguing, that the velocity should depend upon the turning radius and the friction alone. So when I solve for the velocity, I find, taking the square root of both sides, a speed of 11.4 meters per second. So how does this speed now allow me to figure out something about how to lean? So the first part was just to figure out how fast can I go. Okay, this is how fast we can go. The next part is, how do I figure out how to lean in order to achieve that speed and make sure that everything is balanced? So notice from the picture, let's go back a few, whoops. from the picture that theta is measured with respect to the vertical. So this is different from our inclined plane problems where we measured theta here, with respect to the horizontal. So let's bear that in mind when we are, trying to figure out what's going to happen to our lean angle. So the lean angle is measured with respect to the vertical. If I draw a parallel line here and create a little reference triangle, I can see that I can identify that this is my theta here, right? Alternate interior angles being equal to one another. So within this little right triangle, I can think about the function, the trigonometric function tangent, and I can see that I've got theta here and opposite and adjacent here, so that tangent of this angle theta is going to be equal to the force of friction divided by the normal force. So, there's nothing different here than if I was just faced with any other vector. These properties are still the same. Whether we're talking about forces, velocities, or what have you, the ratio of this force to this one should be the tangent of that angle, since I'm making a right triangle here. When I plug in that the frictional force is equal to mu times the normal force, I can see that these normal forces actually cancel out. And so that the only thing this lean angle depends upon is whatever this frictional coefficient is. So plugging in what the value was for the frictional coefficient and then taking the inverse tangent in order to solve, I find an angle of 47.7, which is a pretty steep angle to have to lean in from the vertical. All right, so that wraps up this lecture. The next lecture we will do one more example of applying Newton's laws, and then we will start discussing Unit 3, in which we take a look at the concepts of work and energy.